In the next example, we'll look at finding the area of a circle r equals 3 sine theta, and outside the cardioid r equals 1 plus sine theta. All right, so probably it's a good idea for us to graph this. So the circle r equals 3 sine theta. Okay, looking at our circles, it's going to be very much like this one, r equals 2 sine theta, but instead of having a diameter of 2, it'll have a diameter of 3, but it'll be up there symmetric around the line theta equals pi over 2. Okay, so one, two, three, so let's make a diameter of 3. Okay. And so that's our circle, and then we have a cardioid, r equals 1 plus sine theta. Okay, so that's going to be very much like this one, where a and b are equal, but instead of going all the way up to 3, it's just going to go up to 1 because that value is 1. Okay, so we're going to have something that looks like that. Okay. And then we want the area of the region that lies inside the circle, so inside the circle but outside the cardioid. So we're looking at this area right here. Okay. And so we know that the area of a region is going to be the integral from a to b of 1/2 r squared d theta. So one of the first things you might want to do is figure out what a and b are. Okay, and so if we were to look at the angles like here and here, because this is the intersection point and this is an intersection point. So really is between the place where that angle, that's the starting, and then it sweeps out all the way around until here. Okay. So in order to find out those points, we need to see where the circle and the cardioid intersect. So since both of these are equal to r, we can look at where 3 sine theta is equal to 1 plus sine theta. Our 2 sine theta is equal to 1, or where sine theta is 1/2. Okay, and we know that the sine is 1/2 and the first and second quadrants at pi over 6 and 5 pi over 6. Okay, and so our area is going to be the integral from pi over 6 to 5 pi over 6 of 1/2 r squared. So thinking about this, like if I do the area, if I do this as my r value, I'll get not only the area in the circle but also this area down here. Okay, so we'll want to do that. Okay, but then we'll need to subtract off this area that's in the cardioid. Okay, so let's do this one. So on this one we'll do the 3 sine of theta squared d theta, and then we're gonna, so that will be the area of the inside the circle, and now we're going to want to subtract off the area that's in the cardioid. So we'll subtract off the area that's in the cardioid, so we'll do 1 plus sine as that r. Okay, so let's pull the 1/2s out, and also we see that the bounds are exactly the same, so we can turn that into a single integral. So this will be 1/2. Okay, the integral from pi over 6 to 5 pi over 6. When we square that, we're going to get 9 sine squared theta, and then we'll subtract off. When we square this, we're going to get 1 plus 2 sine theta plus sine squared theta. Okay, so let's simplify this term. And then also, we can use some of the symmetry here. Notice that because both of these are symmetric over the line theta equals pi over 2, we could just, instead of going from pi over 6 to 5 pi over 6, we could just go from pi over 6 to pi over 2 and then just double that. So that'll just be a little bit easier in terms of having to evaluate sines and cosines. So we're just going to do 1/2 and then double the integral from pi over 6 to pi over 2. And then simplifying in here, we've got 9 sine squared and then minus sine squared. That'll give us 8 sine squared. And then we've got a minus 2 sine and then a minus 1. Okay, so that's just the integral from pi over 6 to pi over 2. And then we need to do a substitution. And if we substitute this, this will be 8 times 1/2, so it's going to be 4 of 1 minus cosine of 2 theta. And then minus 2 sine theta minus 1. Alright, let's simplify one more time, and then I think we'll be good to do our integral. So we're going to distribute that 4. We'll get 4 minus 1 is 3. And then minus 4 cosine 2 theta. And then minus sine 2 theta, or just a theta. Alright, I think we're ready to integrate now. Alright, so the integral of 3 will be 3 theta. Of 4 cosine 2 theta, that would be 1/2 sine of 2 theta, but if we multiply that by 4, we'll get 2 sine of 2 theta. And then the integral of sine is negative cosine, so this will give us plus 2 cosine theta. And then that will be integrated from, or evaluated from pi over 6 to pi over 2. Okay, so when we put pi over 2 there, we're going to get 3 pi over 2 minus, let's see, the sine. So when we put pi over 2 in there, we're going to get the sine of pi. The sine of pi is just 0, so that'll be 0. And then plus 2 times the cosine of pi over 2. Well, the cosine pi over 2 is 0, so that'll just be 0. And then when we put pi over 6, we're going to get 3 pi over 6 is pi over 2. And then minus, okay, and then we'll have 2 times the sine of pi over 3. The sine of pi over 3 is square root of 3 over 2. And then plus 2 times the cosine of pi over 6. The cosine pi over 6 is square root of 3 over 2. Okay, so these cancel, that's just 0. So that gives us 3 pi over 2 minus pi over 2, which is 2 pi over 2, or just pi. Okay. So that is the area of the region that's inside the circle and outside the cardioid. Now that example just gives us an idea of if we wanted to do the area that was bounded by 2 polar curves. Okay, so in the previous example, what we did is we took the curve on the outside, which was the circle, and we subtracted the curve that was on the inside. So, and that, in our case, that was the cardioid, right? So if we do for the circle, you would get the whole entire thing, and then for the one on the inside, you get that part. So if you subtract them, you'll just get the part that's bounded between the 2 curves. Okay, so this is basically what we did in the last example, and then we realized, well, the bounds are the same. We factored out the 1/2, kept the bounds, and just did like g squared minus f squared. Okay, so that is a general way of doing the area bounded by two polar curves. Okay. Now when we did that example, when we looked at the area for between those two polar curves, we had to find the intersection points to figure out, what the bounds of our integral should be. But the fact that a single point in a polar plane has many different representations, sometimes it makes it difficult to find all the points of intersection between two polar curves. So, for instance, we might say, well, how many points of intersection are there between the circle r equals 2 sine theta and the cardioid r equals 1 plus sine theta that we just did in example 2? Okay, so when we solved the equations, we found, this point here, pi over 6, and then I guess that would be, so 1/2 pi over 6, and this point over here, which is 1/2 5 pi over 6. Okay, but if you look at the, sorry, you couldn't see that, but if you look carefully at the picture, the circle goes through the origin and the cardioid also goes through the origin. But when we solved the equations, we didn't find that point. Okay, so let's look at why that happened. Why? So there are clearly 3 points of intersection when we look at the graph, the picture of the graph. But when we solved the system, we only got 2 intersection points. So here's the difficulty. So the origin can be represented by an infinite number of different, it can be 0 and then anything. Okay, so any angle and then go out 0 from the origin, you're always going to get the origin. Okay, and so when we look at the circle, okay, the circle, like when we draw it, we start here at 0 degrees and go around, and then it gets back here at 2 pi degrees, or 2 radians. Okay, and so we start at the point 0, 0, and then we go around and we reach it again, and then that should have been 2 pi. I believe. Sorry, that should have been 2 pi. All right, and then but if we look at the other one, at the cardioid, okay, so the cardioid starts here at this point, okay, when theta is 0, and then it comes around and it reaches the origin at 3 pi over 2. Okay, so 0, 3 pi over 2 is the spot where we reach the origin. And so the values that satisfy this equation are 0, 0, and 0, 2 pi. What satisfies this equation is 0 and 3 pi over 2. Now, these are all just different ways to represent the origin. Okay, but because they're not the same, we never find that point. And here's the issue. So there's a sort of this idea of looking at different angles, or let's just call that a different time. So within as you're drawing, tracing through the curve. So the points don't collide at the same angle. Okay, so they reach the origin at different times. But the curves actually do both go through the origin. So in terms of just looking at the curves that are drawn, they both contain the origin, and we should say that the origin is a point of intersection. Okay. And so, if we want to find all the points of intersection, it's really helpful to sketch the graphs, because if you just solve the equations like we did back here, you might not and probably won't find all of the intersection points. Okay, so let's look at an example. Okay, so we want to find all of the intersection points of the curves r equals cosine 2 theta and r equals 1/2. Okay, so grabbing our sheet, r equals cosine of 2 theta. When we have a multiple of theta, coefficient on theta, that's when we get these rose curves. Okay, and so cosine of 2 theta, so cosine is, here's an example of one with an even. Okay, so we're going to get twice the number of petals, and it's going to be symmetric around the polar axis. Okay, so we're going to get 4 petals. Let me draw. let's say this is 1, 1. Okay, so we're going to get 4 petals and they're going to be symmetric about the polar axis. So we'll have something that looks like this. Okay. And then, then this one, r equals 1/2. Well, that one's not on here. That one's easy. Okay, here's 1/2 and 1/2 and 1/2 and 1/2, and it doesn't matter what the angle is, we always just have a radius of 1/2, so we get a circle. Okay, so if we look at those two graphs, we're expecting to get 1, 2, 3, 4, 5, 6, 7, 8 different intersection points. Okay, and so let's just go ahead and, if we want to find intersection points, usually we just solve the system of equations. Well, they're both r, so we just want to look where cosine of 2 theta is equal to 1/2, and for both of these, theta is between 0 and 2 pi. So they both take 2 pi to make a complete, before they repeat themselves. Okay, and so if we take the inverse cosine of both sides, well, the cosine is 1/2 in the first and fourth quadrant, so that'll be at pi over 3 and at 5 pi over 3. Okay, and then if we multiply everything by 1/2, that will give us that we've got pi over 6 and then 5 pi over 6. And since we're going from 0 to 2 pi, the period of this is pi, so we need to add pi to give us every angle in that. And so if we add another pi to this one, we'll get 7 pi over 6. And if we add another pi with a period to this one, we'll get 11 pi over 6. Okay. And so we should have intersection points, okay, where we have pi over 6 radians, 1/1/2. Okay, that's this one right here. This one is 1/2 pi over 6. And then we should get 5 pi over 6 1/2. That's this one. And then we should get 7 pi over 6 1/2. That's this one. And finally, we have 11 pi over 6 with 1/2, and that's this point over here. Okay. And so notice, we've got those 4 by solving it simultaneously, but these other 4 points don't show up when we solve the equations, solve the system of equations. Okay, so, but what is it? Let's just see what it looks like. So it looks like this, pi over 3 would be this angle right here. So let's see what happens at pi over 3. Okay, so in this equation right here, r is going to be the cosine of 2 times pi over 3. Okay, so our r value is equal to, so the cosine of 2 pi over 3, well, that's in the second quadrant. It's negative in the second quadrant, so we're going to get negative 1/2. So at pi over 3, we have a negative 1/2. That's the point that satisfies, this first equation. And so pi over 3 negative 1/2, that's actually this point down here. Okay. But when you go to this equation, okay, well, because r is negative 1/2, that doesn't equal 1/2. We don't see that. But if you think about it, the r equals negative 1/2. If I were to draw that circle, it's exactly the same circle as the original one. Okay, so so this one, no matter, you know, what, you have a distance of -1/2 from the origin. Or you just go in the other direction, but you still get the same exact circle. So these are the same circle. Okay. So when we solve using this one, we're only going to find the points where we get a +1/2. And we would also need to, you can just use the symmetries. If you draw the picture and you see it to be, you can just draw the pictures, or you could solve the equation for -1/2. But we'll see, you know, we're going to have this pi/3 1/2. Okay, this is just another representation of you know, that really came from this angle, 4pi/3 and 1/2. Sorry, -1/2. Okay, so -1/2 4pi/3 satisfies this equation. Okay, so we could represent it that way, but we'll choose this representation instead, because then it's a little bit easier to see that actually the R value is 1/2. Okay, so that is okay. So that takes care of you know, this point, I guess we'll call it. And then this one over here, that one's going to be 1/2 with 2pi/3. Okay, now this doesn't actually satisfy this equation. We're going to get a -1/2 there, but it's just another representation of if we had used 5pi/6 instead. And then here for 1/2, this one is 4pi/3. And then this one out here, we need a 5pi/3. Okay, and the thing that's tricky for these, of course, is that this set of point, like if I just plug these angles in, I'm getting a -1/2, not a +1/2. But they're just different representations for actual points, like -1/2, 4pi/3, -1/2, pi/3, -1/2, 5pi/3, whatever ones I missed. Okay, so they're just other representations of those same points. Okay, but we'll probably just list them this way. Okay. That was our, okay, oh, here's last example of areas and finding intersections of points, and we want to finish up this section by looking at the way to find arc length. Okay, so we know that we've already done this with parametric equations, so we'll borrow what we know from parametric equations. So if we want to find the length of a portion of a polar curve, r equals some function of theta, we're just going to treat theta as a parameter and write the parametric equations. So we know that x is r cosine of theta, and that y is r sine of theta. Okay. And then when we have parametric equations, we know that the way that we find the arc length is to take the integral between the two values, alpha and beta, of the derivative of x with respect to its parameter squared, plus the derivative with respect to its parameter squared, square root the whole thing, okay, dt, or whatever the parameter is. Now our parameter is cosine instead, so we'll just have to change all of our t's to thetas, but that we know how to find arc length, and since we've written these in parametric form, we can easily just use this result. Okay, so let's figure out what dx d theta would be. Okay, so we've got a product here, so we need to do the first times the derivative of the second, so that would be negative sine of theta plus the second times the derivative of the first, so dr d theta. Okay. And while we're at it, since we need that squared, let's go ahead and square it. So let's do dx d theta squared. So if I square this, okay, I don't want to lose the negative sign, so if it'll be this squared, so that will be r squared sine squared theta, and then minus 2 r sine theta cosine theta dr d theta, and then square this, we'll have cosine squared theta dr d theta squared. All right, and now let's do dy d theta. So that'll be the first times the derivative of the second plus the second times the derivative of the first. And let's square this one too. So if we square this one, okay, we'll get r squared cosine squared plus twice their product, so that'll be r sine theta cosine theta dr d theta, and then square that one, so we have sine squared theta dr d theta squared. Okay, and so if we want to find the arc length, that will be the integral from alpha to beta of the square root, and then we want to add these two, so dx d theta squared plus dy d theta squared. Okay, so let's add, so we'll add these two, so we're going to get r squared sine squared theta plus r squared cosine squared theta. And then we add these two. These are exactly the same, but with one's positive, one negative. Those will cancel. And then we'll have these two. Make this a little bit longer. So we'll have cosine squared theta dr d theta squared and sine squared theta dr d theta squared. All right. Okay, so and here, if we factored out an r squared from the first two terms, we'll have r squared times sine squared plus cosine squared. And here, if we factor out the common dr d theta squared, then we'll have cosine squared plus sine squared. Okay, well this is just one, this is just one, so this gives us, okay, the square root of, so we still have r squared times 1, and we have dr d theta squared times 1. Okay, so this will be our formula for finding arc length. Okay, so square the function, whatever we get for r squared, plus the square of the derivative with respect to the parameter theta, and square root. All right, so let's look at an example of that. So we want to find the length of the cardioid, 1 plus sine theta. So once again, it's probably helpful to draw it. So let's look at our picture. So when we have a cosine, the cardioid, you know, is a left-right kind of thing. When we have sine, it's like this one, right? Okay. So our cardioid is going to look like this. Okay. And so we want to find the arc length. Okay, well it takes the entire, so theta gets to go between 0 and 2 pi to make, and then it'll start repeating. So those will be our alpha and beta. So we go from 0 to 2 pi. And then the square root of r squared. Well, our r is 1 plus sine of theta. And then plus dr d theta, so we need to take the derivative. The derivative of this one is cosine theta, and that needs to be squared. Okay, so that will be the integral from 0 to 2 pi. Okay, when we square this, we're going to get 1 plus 2 sine theta plus sine squared theta. And then this one squared is cosine squared. Sine squared plus cosine squared is 1. So when we simplify this, we're just going to get 2 plus 2 sine theta. Okay, so we could factor the 2 out. Let's take the square root of 2 out, so that we're just left with 1 plus the sine of theta. Okay. And then this is a little bit of a tricky integral to do, but what we can do is multiply this by the square root of 1 minus sine of theta over the square root of 1 minus sine theta. Okay, and then that will give us in the numerator the square root of 1 minus sine theta times, 1 plus sine theta times 1 minus sine theta is 1 minus sine squared theta. And then in the denominator we just have minus sine theta. Okay, and since this is cosine squared, when we take the square root, we're going to need to do the absolute value of the cosine of theta over the square root of 1 minus sine theta. Okay, now this is a little bit tricky to do the absolute value. So if you think about, let's think about the graph of the cosine. Okay, well, sometimes it's positive, sometimes it's negative. So to do the absolute value, we have to sort of break this up into intervals. Okay, so for it being positive, if we go from 0 to pi over 2, we'll get the positive value. So from 0 to pi over 2, cosine will be positive, so we can use cosine of theta over a square root of 1 minus sine theta. But between pi over 2 and 3 pi over 2, it's negative. So we would have to do from pi over 2 to 3 pi over 2. We'd have to put negative cosine of theta over square root 1 minus sine theta, d theta. And then from 3 pi over 2 to 2 pi, it's positive again, so we can just use cosine theta. Okay. Now there's a lot of ways we can, these are also close, but we can just take the minus and put it outside there instead. So if I change this to a minus and change this to a plus, that way the integral inside there is the same, and we can kind of just consider that once, and then we'll just have to look at the various different bounds. Okay, and so the trick on this one is just doing the right substitution. Okay, so on this one, we'll let u equal the square root of 1 minus sine theta. Or another way to write that is 1 minus sine theta to the 1/2 power. Okay. And so then du is equal to, if we think of it this way, is going to be 1/2 of 1 minus sine theta to the 1/2 minus 1, which is negative 1/2, times the derivative of the inside, and the derivative of the inside is negative cosine theta. So du is equal to, I'm going to put the negative, well, let's make a little fraction here. Okay, so negative 1/2, so the negative is there. And then cosine theta is in the numerator, and this is a negative, so put that in the denominator and rewrite that as 1 minus sine theta. Oops, I forgot to put d theta. Okay. So what's really, really nice about that is we basically have this right here, and here, and here. Okay, so if I just multiply both sides by -2, I would have -2 du equals this cosine theta over square root of 1 minus sine theta d theta. So in all of these, for cosine of over square root of 1 minus sine theta, I can just substitute in -2 du. Alright, so let's go ahead and do that. So that'll be the integral from 0 to pi over 2 of -2 du. Oops, I forgot to change my bounds. That can't be 0 to pi over 2. We'll have to go change our bounds in a second. And then I'll do minus. Let's look at the bounds there. This will be minus 2 du. And then plus this integral of -2 du. All right, but we do need to change our bounds. Okay, so let's let me make this theta and this u. Sorry. Okay, so theta here went from 0 to pi over 2. Okay, so when theta is 0, the sign of 0 is 0. We'll have the square root of 1, which is 1. And when theta is pi over 2, the sign of pi over 2 is 1. 1 minus 1 is 0. The square root of 0 is 0. So this one will be from 1 to 0. Okay, this one, pi over 2, that was 0. Okay, and then 3 pi over 2. Let's look at that one. Okay, so the sign of 3 over 2 is -1. So this will be 1 minus -1 is 2, so this will be square root of 2. And then our final bound was 2 pi. So the sign of 2 pi is 0. 1 minus 0 is 1, so this is going to be 1 again. Okay. Okay. So let's go ahead and let's just factor the -2 out of all of these. I think that might make it the easiest to put the -2 out here. Okay, and so if we take the -2 out, we're just going to be left with du, and the integral of du is just u. So this will be u evaluated from 1 to 0, and then minus u evaluated from 0 to square root of 2, plus, and this will be u evaluated from square root of 2 to 1. Alright, so this one will be -2 square root of 2 times, well, this one will be 0 minus 1, which is -1, and then minus, and this will be square root of 2 minus 0, that's square root of 2, and then plus, and this one will be 1 minus the square root of 2. Okay, and so -1 plus 1 is 0, those go away. This will give me -2 square root of 2, so I have -2 square root of 2 times -2 square root of 2, which is 8. So the arc length of the cardioid is 8. Okay. All right, so that wraps up chapter 10 for us.